All right, good morning, everyone. Y'all ready? Okay, we have a test on Wednesday, right? So we will be talking today about integration by parts. I couldn't remember and I didn't watch the video. Did I tell y'all for sure whether or not this would be on the test or not?
I think you said we'll decide today.
Yeah, I think what we'll do is there's like easy problems when it comes to integration by parts, or I should say easier, and then there's harder ones. I believe what I plan on doing is just putting maybe 2 easier ones on there. And let's just go through this today, and then hopefully you'll agree that maybe they're easier. I don't know, we'll see. But are there any questions over anything before I get started? We're okay?
Actually, I had a question about the homework assignments.
Yes.
So yesterday I didn't realize if it was due Sunday or on the day of the test, but I think it was due at 11:55 or 11:59 last night.
Yeah.
I tried to put extensions for one of them, but it said it wasn't available for the assignment. I was just curious if we had to wait for the test day to pass before we could put an extension on it.
Should have automatically done that. Here, let me just write this down. After class, I'll look at that.
Sure.
Okay. Anything else? Okay, so let's just recap where we are on things. Of course, when we first started antiderivatives, we said if it's possible that it's something we know from Cal 1, we can take care of it, right? Antiderivative of cosine is sine, right? We know if we have x to a power, we can take the antiderivative using power rule. And then we learned that there's this thing called substitution that allows us to take care of certain integrals where we can see something in its derivative. But even in that, we saw that sometimes you can do substitution when it's not even that natural to do the substitution. It still might work. That's where we are. Now, before I begin the integration by parts, I wanted to show you a couple of things with substitution that we're going to be needing. They're going to come up quite a bit. So kind of a little shortcut. Not short. In certain instances, we have a shortcut. So let's look at the antiderivative cosine x dx. Oh, let me record. Oh, you know what? It is recording. Never mind. Okay, I set it up to automatically record. Okay, so we all know the antiderivative of this is sine x dx. Okay, now let's look at a different example. What if instead of cosine x, we put cosine 3x? Well, we know the antiderivative has to have sine 3x in it because the derivative of sine of 3x would be cosine of 3x, right? But with chain rule, you would also get a 3 to come out, wouldn't you? And over in the integrand, we don't have a 3. So what I would need to do is scale by 1/3 here. Do y'all agree with that? Do y'all see that? Okay. I see some nodding of the head. So you're just going to need to let me know if it's not making sense. You know, if I put like negative 10x here, dx, inside the cosine, then again, I know I'm going to need sine of negative 10 dx, or I mean negative 10x plus c, but that negative 10 is going to pop out. So what am I going to need to put out front in order to kind of counteract that negative 10 that pops out?
Negative 1/10?
Yeah, negative 1/10. Okay, so it's basically the reciprocal of what's in front there. Let me do another one. Cosine of, how about if I go negative 10x plus 4 dx? Well, we know the antiderivative of that's going to have to be sine of negative 10x plus 4 plus c. Now, what's going to pop out this time, and what can I do to counteract it?
Wouldn't it still be the negative 1/10?
yeah, it's still negative 1 over 10. So by me adding that 4 in there, that really didn't change anything, did it? Because when I take the derivative on the right side and I do the chain rule and do the derivative of what's in there, the 4 doesn't come into play, does it? Because it's a constant, so derivative of that's going to be 0. So maybe we can generalize this. Let's say we had the antiderivative of cosine, and inside of it, let's say we have a linear expression, ax plus b dx. So pay attention, this is linear, right? That's a linear expression in x. What I know is that the antiderivative will be sine of that linear expression plus some constant, but then I have to scale it. I have to scale it by what? Or what do I
1
need
over
out?
a.
1 over a. 1 over a. Okay, and that's almost kind of like a general formula. Anytime you have a function with a linear expression in it, when you take the antiderivative, you will always have to scale out by 1 over a. Let me give you a different example. What if you have e to the negative pi x plus 1 dx? So does everybody see that what's here in yellow is a linear expression in x? You'll see that? Okay, so the antiderivative of e raised to anything is itself. So I know the antiderivative of this is itself plus a constant, but I have to account for a negative pi that's going to pop out, right? So I've got to scale this by a negative 1 over pi. Remember, pi is a constant, just like the number 4, right? It's just a number. And that would work for any function that has a linear, any function that is composed with a linear expression, you would always have to scale by 1 over a. Does that kind of make sense? Okay, I'll give you one more. So when you look at that, what you should be seeing is something that looks like this. Right, something like that, like you should be thinking arctan. Now, this part right here is linear. The part that's being squared is like the u, it's linear. So I know that the antiderivative of this is going to be arctangent of that linear expression plus c, but then I have to scale by 1/3. Again, because there's a 3 in front of that x that would pop out in the chain rule. Okay, does this all kind of make sense? All right, so this is going to come up a lot now, and this step, you know, when I do these antiderivatives, I'm not going to talk about it anymore. I'm just going to be like, oh, and we scale by whatever it is we scale by, right? So we're good? Sure. Okay. All right, now back to, or let's get to integration by parts. So I started this out. Integration by parts, called IBP, integration by parts, that's the abbreviation that I use for it. Most textbooks do that also. This formula, which I have not given you, I started to write some things here. This formula is a formula that allows us to transfer a derivative. And right now that should make no sense to you, okay? But I'm going to refer back to that in a moment. So what you see here in red is something that we're coming into today's class, we know this already. If we have the sum or difference of two functions and we want to find the antiderivative, we can just split it up and do them separately. And that's a great thing, right? The question, right, the question mark here is if we have two functions being multiplied, can we split it up into multiplication of the antiderivatives? So can we do them separately, find the antiderivatives, and then make that our answer? And you already know the answer to this is no. I told you this already. But let's convince ourselves why it's not. So I gave a specific example. We have two functions. We have x and we have sine of x. And there's multiplication between them. So what we're going to do is we're going to do one integral where we do the antiderivative of sine x, and the other one we do the antiderivative of sine. We go ahead and work those out. There's your antiderivatives. put them together. And so the question is that the answer? So how could we check?
Take the derivative.
Take the derivative. So I'm going to take the derivative of this real quick, and I'm going to remember there's a product rule right there. So I'm going to take derivative of the first one, which is going to give me negative 2x, times the second one, plus the derivative of the second one, times the first one. Okay, so that's me doing the product rule there. And if I clean this up, the question is that the original integrand? And the answer is no. So it doesn't work, right? That's one good thing about math. If you're ever checking to see if something is true, if you can just find one example where it's not, then you know it's not true. So this formula, there's no way it can be true. So that means, you know, we don't have a way of doing products yet, okay? So that's where integration by parts comes in. So here's the idea behind integration by parts. First thing I'm gonna do is I'm gonna change some notation for us. So you know how I've been using f and g as two different functions? From now on, I'm gonna write u is gonna be some function of x, and v is some other function of x. Okay, so u is some function f of x, and v is some other function g of x. So in the previous example, this is kind of like this was the x, and this was the sine x. And I'll put that problem up there as a reminder of something we'd like to be able to solve. Wait, was it cosine? No, it was sine. Yeah, that was. So that was a problem that I had just done, and we realized that it doesn't work the way we wish it would work. And so we're stuck. Okay, so in general, we have two functions, u and v, all right? And the question becomes, if we have u times v, you know, what's the antiderivative of this, right? And we'd have to put with respect to x here, all right, dx. All right, so watch what I'm gonna do. I'm gonna start out back in Cal 1. Let's say I had two functions, u times v, and I asked us to take the derivative, all right? Well, you would use the product rule, wouldn't you? And you would say, this is the derivative of u times v plus the derivative of v times u. That would be our product rule, right? Okay, so we started out with u times v, and then we took the derivative. Now I'd like for you to take the antiderivative, which seems like, why in the world would you want to do that? Okay, so we take the antiderivative over here, and we take the antiderivative over here. Now, on the right side, we have a plus sign, right? Which means we can do them individually, can't we? So when I say take the antiderivative on both sides, I'm actually going to put another integral sign there. You all right with that? Okay, now, on the left side, think about this. You have u times v. You took its derivative and then its antiderivative. So what should that give you back?
Just regular u times v.
Just
The
u times
regular
v. Yeah, just u times v. It's like you differentiated it and then you integrated it. So it should be back to what it started as. That's just u times v. And now this is equal to integral. Now I'm going to change the order of things here because multiplication can be changed. And you might ask me why. Just hang tight. It's coming. Okay. So I just kind of commuted the things inside those integrals. All right, now the critical part. This is the critical part. I'm going to take this integral. Well, you know what? I'm gonna leave this integral here. I'm gonna take this integral and move it to that side of the equal sign. And to do that, I just subtract it on both sides. So what we'll be left with is u times v minus the integral of v times u prime equals the integral of u times v prime. And then one more step, I'm going to switch it. So like, you know, if you write x equals 4, that's the same as writing 4 equals x. It doesn't matter which way you write an equation. So I'm just gonna reverse everything. And I'm going to do also one more thing while I'm writing that. Okay, so notice what I did here. I changed, it's just notation that I changed. This u prime really means the derivative of u, right? And instead of writing u prime, I wrote du. So it's just a little change in notation, that's all. And again, you'll see why I'm doing that change in notation in a second. That's your v prime is now dv, all right? Any questions on that? Just algebraically, what I've done? Okay. Gonna rewrite, even though you don't need to rewrite it. I just want to have it one more time. All right, this is the integration by parts formula. Now, there's something very important about the integration by parts formula that you need to understand. The integration by parts formula does not allow you to take an integral that someone gives you, and this is not a formula that solves that integral, okay? It does not solve it. What it does is it transforms the integral you're starting with into two things. The first thing it transforms it into is just the product of two things. There's no antiderivatives involved at all. Do y'all see that? And then the second piece it transforms it into is a new integral. Okay, so you start out with the original integral. And then the formula allows you to transform it into this thing out front minus some new integral. So you might be saying to yourself, well, why would I want to start with an integral and turn it into a new integral? Well, there's something very different about these two integrals. Do y'all see the differences? Let's take a look at the differences in this integral, or between these two integrals. In the original integral, you have something u, right? And remember what u was, right? U was what? Some function of x, right? So you got some function of x sitting there in the original integral. And next to it, you have dv. Now what's dv? dv would be the derivative of some other function g, okay? So your original integral has a function of x in it, right? And the derivative of some other function. Don't confuse that with substitution. Remember, substitution, you were looking for something and its derivative, right? This is saying that you have an integral where you have a function, and next to it, the derivative of some other function. Doesn't even have to be related to the u. Now, in the new integral, what happens? Look what happens to the u. In the new integral, the u becomes what? Du, right? And then the dv becomes v. So do you see that they transferred the derivative, right? The u now becomes u prime, or du, and the one that you were looking at that was the derivative of something, in the new integral, it's actually its antiderivative. Now that may seem like, why in the world would you ever want that, right? Why would you ever want that? But let's see how it works, okay? It's going to become very useful. This transferring of the derivative, all right? So let's go ahead and let me remind you that that formula is actually formula number 1 on reference page 6. U dv is equal to uv minus integral v du. Oh, and I forgot to tell you the cute little way you can remember it. So the cute way you can remember this is a little saying. Ultraviolet minus voodoo. Okay, so that's the way it was taught to me, and a lot of Cal 2 students learn this. It's this formula. It's the right-hand side of the integration by parts formula. It's ultraviolet minus voodoo, all right? Now you have to remember the integral sign, okay? Ultraviolet minus the integral of voodoo. Are y'all ready to do your first example of integration by parts? All right, here we go. So let's go with the one that we were stuck on. All right, so things are starting to get more complicated because now we have the stuff from Cal 1, we have the power rule, and we have substitution, and now integration by parts. So there's kind of like 4 things that we've already got in our little like Rolodex of like, how do we go about attacking these integrals? And it's going to get harder because we're going to add another, there's going to be another, let's see, we have trig integrals, trig sub, partial fractions. I'm missing one. Anyway, we're going to add at least 3 more to this. So that's what's going to make exam 2 difficult. Exam 2 is going to be hard because you're going to have an integral and there's going to be nothing there to tell you what to use. And so you may be sitting there trying one method and then you realize, oh crap, that was just use substitution. So the only way you get good at that is practice, 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 practice. As many problems as you can do, all right? Okay, here we go. So we look at this, we go, okay, we can't do anything that we've tried. I mean, maybe you can try substitution, but I don't see something and its derivative there. So to save us time, let's go to integration by parts. Now, if we're going to use integration by parts, we have to decide which of these pieces in the integrand is our u and which one is our dv. Okay, so we have to pick the yellow and the green here. We have the freedom to do that. We get to choose. Now we have multiplication happening here, right? It's x times sine x times dx. So I have a question. What would you like to choose to be your u? And I'd like some reasoning behind it. Anybody?
X.
Okay, so why x? Is there any, just like it sounds good, or?
I think it's because it's alone and the u is alone, and then for dv it has 2 variables, and then sine of x is 2.
Okay. Stephanie, what happens to u in the integration by parts formula? In the new integral, what are you looking at? Are you looking at u anymore? What are you looking at?
At the v and the d mostly, the dv.
Okay, so look at the, what did I say happens in integration by parts formula? The u in the new integral becomes what?
Derivative.
The derivative of u, right? Right? So Stephanie said, let's pick x to be our u, right? Well, what would that become in the new integral?
1.
1, right? And wouldn't it be great to have a 1 there instead of an x? Like it becomes less complicated, doesn't it? So if we choose our x to be u, then that forces us to make the sine x dx, all of that together, the dv. Now, we know that the x is going to become a 1 in the new integral, right? What does the sine x dx become in the new integral?
It doesn't change.
Careful. Look at what happens to dv here. What happens to dv in the new integral?
Become negative cosine.
It becomes the antiderivative of it, right? It goes from dv to v. See how they're switching places in the 2 different integrals? So when you're looking at this green here, like Stephanie said, let's let x be the u, and we're happy because in the new integral it's a 1. But that means the dv, we need to be able to find the antiderivative of it. What's the antiderivative of sine x dx? I heard someone say it. Was that you, Varun?
Was it negative cosine?
It's negative cosine. So whoever said that, I'm sorry if I missed it. So can you like close it? You don't have to close your eyes, but can you like imagine that your new integral is going to be a 1 and then negative cosine x dx? Can you see that? Like, that's a good integral because you can do the antiderivative of negative cosine x. It's a better integral to work with. So we're going to do that, but we have a formal way of doing it, kind of a systematic way that kind of helps keep track of everything. So this is the way I've always done it. Different instructors do it different ways. I always do integration by parts. I started out by putting a table, just like this. And in the top left of the table, I put u. In the bottom right, I put dv. Okay? Every integration by parts problem that I do, I'm going to set up with that table. Now, we're going to choose our u. We already did that, right? X. And we're going to choose our dv, which is going to be sine x dx. And the way that this table works, the way I like to use it, is that when you're filling out the table, when you're going down, you're taking derivatives. And when you're going up, you're doing antiderivatives or integrals. Okay, so think about if I want to fill out this part of the table below the u, that means I'm going to take derivative du, and the derivative of x we said is 1, right? I'm actually going to put 1 dx. Now the dx comes from the same thing that we did when we were doing substitution. When u was x, we took the derivative with respect to x on both sides, got 1, and then we brought the dx over. Is that okay? So I'm not writing that out. I'm just putting, just don't forget you need the dx there. No matter what, you're always going to have a dx right there. Okay, now I'm going to go over here and I'm going to look at this sine x dx. I'm going to go up to v, right? If I take the antiderivative of dv, that's going to give me v back. And the antiderivative of that is just negative cosine x. Now I'm supposed to put plus c, right? But I'm going to do an integral, and I'm just going to remember at the very end, I'm just going to do a plus c at the end of everything, okay? All right, we got this? Once you fill this table out, you're ready to go. You're ready to actually apply the integration by parts formula. So this integral is going to become, all right, first thing, u times v, right? U times v. So if I look at my table, it's the two things across the top. You're just going to multiply those two together. And that should give me negative x cosine x. And then the next part of the formula is a minus, and then an integral. And now the integral is v times du, which will always be this with this, but like diagonally across. That will always be the voodoo part. And when I put those together, all I get is negative cosine x dx. I don't need the 1, but I do need the dx. Are y'all with me? Yes? Okay, let me just clean up one thing here before we do an antiderivative. I have a negative here and a negative here. I'm going to pull the negative out of the integral. It's going to change that minus to a plus. And then finally, it is time for an antiderivative, right? So like before we actually do this antiderivative, let's appreciate what integration by parts has allowed us to do. It's allowed us to take a complicated integral that we don't know how to find the antiderivative and transform it into this crap out front, right? Minus this new integral. And the new integral is doable now, right? It's something we can actually handle. And that's the beauty of the integration by parts, is that oftentimes you can take a tough integral and you can make it easier. You still have to do integration. It's not just like it's not like the quadratic formula where you just like use the formula and there's your answer. You still have to do work. It's just the work you have to do should be easier. Okay, x cosine x. Don't have to do anything there. Antiderivative of cosine x is sine x. Antiderivative, not derivative, right? Plus c. There it is. See how I did the plus C? I just remembered that it needed to be there. Could we check our answer? Yeah, let's take a quick derivative of this. I have a product rule here, and then I have addition, so I can do those separately. When I do the product rule there, I get 1 times cosine x plus derivative of cosine x is negative sine x times x. That takes care of the product rule. And then I still need to take derivative of the sine, which is going to be cosine. And this is, wait, hold on. What am I missing?
I'm a little bit curious how the negative sign in front of the x cosine x wasn't there anymore for the second to
Wait,
last
what?
step. How it went from negative x cosine x minus the integral of negative cosine x.
Okay, yes. Okay, my apologies. Everyone, I just wrote it down wrong. And I was finding that out right now. Y'all speak up when I do something ridiculous like that. That negative right there, I just forgot to bring it down. Y'all see that? Okay, and I was about to run into problems right now. I could tell there was something wrong. I'm gonna have to redo that product rule. Okay, let me redo that. See, we all make mistakes, right? We're all human. I'm just not the one who's getting graded for it anymore. Plus negative sine x times negative x. Okay, that changed things quite a bit. Y'all agree with that? Derivative of negative x is negative 1 times cosine x plus derivative of cosine x is negative sine x times negative x, and then the last piece over there. Now, when we clean this up, this is negative cosine x, and then that's going to be 2 negatives there are going to be positive x sine x, and then plus cosine x, and the cosine x's cancel. And you're left with x sine x. So it works, right? It works out. Okay, what do y'all think? Eh? Shall we do another? How about this? You know what? Let's not do that one yet. So I'll let you sit there and look at it for a second. Think about it. You're like, okay, this isn't something from Cal 1. Power rule is not going to work because that sign is attached to it. Basic U substitution. Do I see something in its derivative? I kind of see something in its derivative. If U is x squared, the derivative of that, you know what? I'm going to let y'all, give me just a second. I was expecting an important phone call. Let me just let them know I'm busy. All right, sorry about that. I had to take my rotors off my truck this morning, and they were calling me to let me know that they can't turn them. So gonna have to get some new rotors, it looks like. All right. So I was saying maybe basic U sub here. If U is x squared, then the derivative of that's 2x dx. Why does that not work? Because I see an x. I'm off by 2, but why is that not going to work?
There's an a in front of the x.
The 2, I can just do 1/2 on both sides.
Well, when you get the new derivative, you're still kind of in the same boat. You still haven't multiplied two different, like 2 different terms.
I see what you're saying, but this still wouldn't work though. Not because of that though. We couldn't even get it to the point where we could rewrite it.
I think it's because it's like it at that point it's not off by a constant, it's off by a variable. Like if there was like if it's x squared sine x with an x there, then maybe, but at that point it's like you're off by an x, not like a 2 or something.
Isn't that x inside the sine function? This
Right,
is
it's
not
part of the sine
10
function.
times x times dx, right? It's not like you can peel that x and dx and put them next to each other like that, right? Which is what this is over here, x times dx. That's not what we have. We have sine of x times dx. So we can't substitute that. Do y'all see what I'm saying? Remember, with u substitution, you have to see something in its derivative, and the derivative cannot be in the denominator, and it cannot be trapped. It is trapped in this case, right? That x is trapped in a sine function. So we cannot use basic u sub. Everyone clear on that? Okay. So what about integration by parts then? Well, if we do that, we have to pick a u, and then we have to pick a dv, right? And we have the freedom to choose however we want to choose. Now, in the previous one, Stephanie picked x, remember? And it was great because when she picked x in the new integral, it became 1, and it made life great. Here, though, we have x squared. So any suggestions? While you're thinking,
Maybe we can have the sine x be the u and the x squared be dv.
okay, we could try the other way. Let's try that just to see what happens. Okay, let's just see what happens. What if we pick the sine x here? Okay, so we have said the sine x is our u, and that means that everything else, the x squared and the dx together, right? Because you can just move that over with multiplication, you can move things around. This right here becomes the x squared dx, like that. All right, let's just see what happens. So now we finish the table out. We go down, we take the derivative of sine x is cosine x dx. And the antiderivative of x squared is 1/3 x cubed. We all good with that? Now, we know that the formula is going to be ultraviolet minus the integral of voodoo, right? I'd like for you to look at voodoo right now. Voodoo is the diagonal, right? Think about that integral. Has it gotten better? Has it gotten worse? What do you think?
Well, it's gotten worse, but would we be able to do integration by parts twice?
Okay, I'm going to say yes and no. Yes, it's gotten better. I mean, sorry. No, it has not gotten better, okay? The new integral is going to have an x cubed in it, where the original one only had x squared, right? So it's like by doing this, we've actually made the power on the x go up, which is not exactly what we want, right? Because we still wouldn't know how to do that integral. Now, the other answer is yes, we can do integration by parts more than once, but we should switch the u and the v, u and the dv when we start. Like we should go, so I wanted us to do this because I wanted you to see how it didn't get better. But what if we had started with u being the x squared and dv being the sine x dx? Let's fill the table out real quick, and then we'll talk about voodoo, the voodoo part. So du is going to be 2x dx, and v will be negative cosine x. Now take a quick look at Voodoo. Has it gotten better? We went from x squared down to 2x, right? And the sine became a cosine thing, but that's okay, right? I mean, we can deal with cosine and sine. So the new integral is going to have an x times the cosine x in it. And it's going to have a -2 out there also, but it got better. And now with that new integral, why don't we do integration by parts again on that new integral? And when we do it a second time, we can take that power from an x down to a 1. Do you see what I'm saying? So because we had an x squared, the first iteration of integration by parts knocks it from x squared down to x, and the second iteration will knock it from x down to 1. Yes? Some of y'all have like stunned looks on your faces. I'm not sure what that is. Okay, this becomes, all right, so I'm using this table right here. The formula says ultraviolet, so we have to do these two multiply across. So I have -x² cosine x, okay, minus, now watch what I'm gonna do here. I'm gonna start doing this more often now. I'm going to leave a space. See the space I left in front of that integral? I'm gonna do that because anytime when I do my voodoo now, right, my voodoo is gonna be these two together. Any constants I have, I'm going to pull out of the integral. So I'm going to pull out, what am I pulling out here? Got a
The 2.
And a negative. Let's pull the negative and the 2 out. And that will become what? A plus now? 2? Does everyone see that? Okay, and then what's still in there is an x, and then a cosine x, and then a dx. Any questions? You'll notice I'm not calling on people right now. It's because we really, you need to see this happen a few times before I can actually ask you for help. Okay, so now we look at this, we say, okay, we started with this original integral and we've got it down to this. Our new integral is better, but still we can't do it yet. So we're gonna look, our entire universe right now is that integral. And we're going to come over here on the side and we're going to do that integral on its own. And we're going to set up another integration by parts formula table. We're going to pick a u, we're going to pick a dv, and we're going to go through the whole game again. This time I'm going to let u be what? X, right? And dv be cosine x dx. And then just fill out the table. So d will be 1 dx, and v will be sine x. And so this integral becomes ultraviolet, which is these two multiplied, minus a little bit of a space there just in case. Integral, and now voodoo. And that's just, ooh, that's just sine x dx. We're happy, aren't we? Aren't we happy? Because now we've got it down to just the antiderivative of sine x. And so I'm going to go ahead and do it. The antiderivative of sine x is negative cosine x. And I'll have a plus c. I'll just throw it on that right now. There we go. All right. So are we ready for the final answer? We've got to take that answer and we've got to stick it right there. And so there's a 2 in front of it, isn't there? We've actually got to distribute a 2 through that. Just bringing that down. Plus 2 times, now you could probably have distributed this without putting it in brackets. All right, so this 2 goes through, right? Goes through and hits all this. Notice that it should have distributed to the c and became a 2c, right? 2 times c. But c is a constant. We don't even know what it is. So twice c is still a constant. So we don't need to actually distribute the 2 through. It's just throw the constant out to the side. And we're almost there. I'm just going to put this together. Negative x squared cosine x plus 2x sine x plus 2 cosine x plus c, box it up. Yeah, nothing there. You can't collect any of those together. Those aren't like terms. But there it is. Could we check the answer? We could. We would have to take the derivative. Do y'all want to? Let's just do it. It'll be fun. Just one time. Okay. So I actually have 2 product rules. I have to do that one and that one. So on the first one, take the derivative. I've got 2x cosine x plus derivative cosine is negative sine times the first function. Okay, plus now the other product rule. Derivative of the first one times the second one plus derivative of sine is cosine x times the first one. And then I have plus 2 times the derivative cosine is negative sine. So I'm going to change that to minus 2 sine x. Okay, there's my derivative. Now this is 2x cosine x plus x squared sine x plus 2 sine x plus 2x cosine x minus 2 sine x. And the 2 sine x's cancel and the 2x cosine x's cancel, and there it is. Yeah, so I mean, think about this. The antiderivative of x squared sine x is way too complicated for, look at that. That's way too complicated for anyone to be able to do in their heads, right? I mean, you have to go through this procedure. But it's amazing because the derivative of that is the original integrand. And see how it just amazingly all works out. All the product rule and all that things cancel, and this magically the x squared sine x appears. It's not magic, but it's pretty remarkable. All right.
So we take the we do the integration by parts until we have x to the x by itself.
Well, this is the first examples, okay? The very first example is just to illustrate how it works, okay? This example is to illustrate how, well, if you have a power of x in front of like sine or cosine or something, it looks like you can do it multiple times and it'll still work. So the only thing I want you to take from this is that the integration by parts formula does allow you to chip away at powers, right? It does. And you can do it more than one time, right? That's all. I don't look too hard for patterns here, like in terms of like an approach you can always use. Let me give you an example of why I don't want to program you to think a certain way. So I'm just making this one up on the fly here to kind of address your question. So if you're in the mindset of, hey, you know, after those other examples, I'm going to let u be x cubed. Because if I do that, I'm going to get it down to x squared. And then when I get that one, I'm going to get that one down to x, and then do it again a third time, and I'll get that x to a 1. So I'm going to do integration by parts 3 times. If that's the way you're thinking, it's actually not going to work here. All right? If you just look at what happens with the table. If u is x cubed, and dv would have to be the natural log of x dx, this part you can do. Du is 3x squared dx. But what's v? What's the antiderivative of natural log? Not the derivative, the antiderivative. We don't know, right? We don't know. We have no idea. Now we'll do it. After this example, I'll do it, and I'll show you what the antiderivative of natural log is. But right now we don't, okay? So let's just try it the other way. If u is natural log x instead, dv is then forced to be the x cubed dx. And you might be thinking to yourself, well, wait a minute, I don't want the dv to be x cubed because when I integrate it, it's going to become 1/4 x to the 4th, and that became more complicated, right? But if you're thinking that way, you're forgetting what u becomes. What does u become? What's the derivative of natural log? 1/x dx, right? And then v now becomes your 1/4 x to the 4th. Now look at voodoo. Now look at voodoo, the diagonal. That's doable. Does everyone see that that's doable? You're going to have 1/x times x to the 4th. One of the x's is going to cancel. It's just going to be x cubed. Can you integrate x cubed? I hope so, right? So this isn't going to work. This one is. Yusuf, do you understand? I'm trying not to, I don't want anyone to get too fixated in one lane. Because as soon as you start thinking that there's like, oh, just anytime I see this, I'm going to do this, you start to become too narrowly focused. You have to be very open to going different directions with these. So great question. Can I proceed? Okay, here we go. So this is now going to become ultraviolet. So 1/4 x to the 4th times natural log of x. So all I did there was those two multiplied across the top. And now I need my minus integral voodoo. So I'm going to go minus some space. All right, what constant, if any, can come out here?
1/4.
1/4. Okay, so I see a 1/4 there. I can bring that out. And then what's left in there, it doesn't matter how you write this. I'm going to write it 1/x times x to the 4th dx. Those two are going to come together and become an x cubed. And I know the antiderivative of x cubed. The antiderivative of x cubed is 1/4 x to the 4th. So we're there. We're pretty much there now. So this is equal to 1/4 x to the 4th natural log x minus 1/4 times, now we're doing the antiderivative, right? Antiderivative of this will be 1/4 again, x to the 4th, and then a plus c, which equals 1/4 x to the 4th natural log x minus 1/16 x to the 4th plus c. What do you think? We could check it, but I'm not going to. So how do y'all feel so far about this? I mean, what's your feeling? Are you starting to get a feeling like at all?
I definitely need to practice.
Yeah, you're definitely gonna need to practice. So I was telling my other class, you know, that I've been teaching Cal 2 since like 2000. I think 2001 was the first year I taught Cal 2. And I never ceased to get excited about it. And it's not because I enjoy doing this over and over and over and over, but this is really about the journey that you were on as my students. You know, like I have the opportunity to show you this, and I never get sick of showing it to you because I know that on your end, you're developing parts of your mind that are, I guess, just maybe you've never had to think a certain way like this or something. You know, this whole class is going to be a journey. Okay, the whole thing is going to be a journey. It's going to be things like this where it's just like, oh, okay, yeah, you know, I guess I could try that. And it's very different than the math that you're used to. I mean, I think it is. It's not formulas and cookie cutter like monkey see, monkey do. You know, I show you this, you just repeat that process. No, this is critical thinking and problem solving. And so I always get excited about it. And so that's why I'm hoping that on your end, you're a little bit uneasy, but at the same time, like motivated to get after the problems now. Like, okay, like I see the formula now. Okay, now I'm gonna need to go use it, and that you have this kind of energy for it, that you're ready to get into it, you know? Let's try and do another one, okay? Because these just keep getting more and more beautiful. All right, here we go. Let's do the natural log, because we've never known what the natural log of x, what the antiderivative is. All right, so you're sitting there looking at it. So can anybody tell me what's different about this one and the ones that we've done before?
There's only one. There's not really an x out in the front or anything.
Yeah, so the integration by parts wants you to find a u and a dv, right? It wants you to come over here and be like, okay, I'm going to pick a u, I'm going to pick a dv. But in this problem, you don't really have two functions, or do you? You have to realize that there's actually, that's natural log of x times 1 dx. And 1 is a function. It's the constant 1 function. So what makes sense to you as what we could pick for our u? And remember, you better be able to take the derivative of it.
U should be the natural log of x.
Let's let u be the natural log of x. And then you can just do a quick little mental check. I need to make sure I can differentiate that. It's 1 over x. Got it. Good. So that's okay in the table. That forces the other part, dv, to be 1 dx, right? Now, you better ask yourself, I better be able to find the antiderivative of 1. And you better be able to find the antiderivative of 1. So this is du is 1 over x dx. And v is x, the antiderivative of 1. A quick little check of voodoo. What is voodoo going to be?
1.
1. And we'll be able to do that. So I think we're happy, aren't we? We're happy to see this. All right, so let's fill it out. This is going to be equal to ultraviolet, so x natural log x. I didn't say this earlier, but I could have written that this way, right? This is the same thing. The reason I don't write it that way is because this is not equal to natural log of x squared. And if you put the x times x next to each other like that, it's dangerous, because then you might think that they're together. They're not. This x is out front, in front of the natural log. That's why I've always written it out in front like that. It's just to avoid that confusion. That x is trapped inside that natural log. Okay, minus a little bit of space, and then voodoo, which is 1 over x times x dx. And that becomes a 1. No constants came out, right? So x natural log x minus the integral of 1 dx. And the antiderivative of 1 is just x, so minus x plus c. There it is. The antiderivative of the natural log of x is x natural log x minus x. On your formula sheets, if you look at your formulas, it's crazy. There's a lot of formulas here, but do you notice that the antiderivative of natural log is not on here? You see that? So you're not supposed to add anything to your formula sheets for the test, but I'm going to officially allow you to add to this just over here on the side. You can go ahead and write that the integral, oops. You can write the integral of natural log of u du is equal to u natural log u minus u plus c. So feel free to add that to your formula sheet, all right? Okay, pretty cool, huh? You know what, on this one, let's make it arcsine of beta x dx. So there, that little b thing in front, beta, is a constant. So I'm not telling you what it is, all right? It's a constant. The variable in the problem is x. Now, what you should be thinking here is that you know the derivative of arcsine of something, right? You know the derivative, but that's not what we're asking. We're asking for the antiderivative, right? So what are you going to choose for u, and what's dv? Or sorry, I put du, that should be dv. So this is kind of like the natural log problem, isn't it? Like you don't have two things, you only really have one thing. So let's go for it. U has to be the arcsine of beta x. You have really no other choice. And that forces the dv to be 1 dx. Now, v will be x, that's the easy part. The du is the harder part. So who wants to tell me what the derivative of arcsine of something is?
Is it 1 over the square root of 1 minus x squared?
Okay, so 1 over the square root of 1 minus whatever the argument of the trig function is, the inverse trig function is, which in this case is beta x, right? So we're going to have beta x squared. Okay, very important next piece. There's something missing still.
dx.
Dx, yep, but you're still missing something. Derivative, chain rule,
Is it times beta?
times beta. Okay, so this beta, everyone, is coming from, you take the derivative of arcsine of something, and that gives you all this. But then you also have to go in here and take the derivative of the beta x, and the derivative of beta x is beta. So that's chain rule. And then the dx, of course, just naturally is there. Y'all good? This is not looking very pretty. All right, let's just do it though. Let's apply the formula. Ultraviolet, x arcsine of beta x minus a little bit of space. Holy crap, look at that. Okay, what, are there any constants that can come out of voodoo?
Beta.
Beta can come out, right? Beta can come out because it's a constant. But that's it, right? That's it. So the only thing left, I mean, what's left there is like a lot of crap, right? There's a lot of crap here. You have an x on top. On the bottom, I don't like that. On the bottom, you have a square root of 1 minus beta x squared dx. Shit, I thought that integration by parts was supposed to make things nicer, right? So let's do some Jeopardy here. The little do. I'm going to give you a minute or two, and then I'm going to call on somebody to see if they have any idea what to do next. 1 minute, maybe 1.5. All right, all right. Coming to the stage is Cheyenne. Cheyenne here?
Yes.
Hi, Cheyenne. How are you doing today?
I'm doing okay.
Okay. All right. Well, you got the lucky call here. Just honest answer, yes or no. You have any idea what to do?
No.
Okay. Ross?
I do have an idea.
Okay. What's your idea?
So could we move the beta back in and then do u substitution from inside that integral?
What would your u substitution be?
Beta x.
Okay. All right. This is getting somewhere. So the key here now is, and Cheyenne, don't feel bad. Okay. Don't feel bad if you didn't know. It's okay. Trust me. There's more than one person here that didn't know what to do. Just don't forget the other things you have, right? You still have u substitution. It's a new integral. So anything that you've done before is on the table now. So the beta, Ross is saying to bring the beta in. I'm not sure. I agree, but I want to do it kind of a different way. I want everyone to look at that beta x squared down here. I'm going to erase it, and I'm going to rewrite it as beta squared x squared, because that's what beta x squared is, right? You're just squaring each one. Now, if I do that, remember, beta squared is a constant. So you have a constant sitting in front of x squared. If you do it that way, then I think it's easier to see a u substitution, because you've got something that's something squared, right? X squared, the derivative of that is 2x, and you actually have x up there, you're off by a constant. You're off by 2, right? Do y'all see that? Okay, so that's what I'm gonna do. I'm gonna rewrite it, and then I'm gonna make a basic u substitution. So this is like new work on the side here. I'm trying to do this integral. So Ross, I'm gonna leave the beta on the outside. You don't actually need it, but you were correct in the sense of a u substitution is the direction to go. So I'm gonna let u be beta squared x squared, that entire thing down there. How about we grab everything? How about we grab 1 minus beta squared x squared, right? Grabbing that 1 with it would actually not change anything, would it? Because the derivative would still be just a constant in front of x. So du here would be weird, but it's -2 beta squared x dx. You'll see where I'm getting that from? Derivative 1 is 0. You still have a minus. Beta squared just comes for the ride. Derivative of x squared is 2x. Okay, now we have an x dx there, so we need to get this x dx by itself. So we scale both sides. Have to multiply by 1 over -2 beta squared on both sides. I would argue that that substitution that we're doing right now is like an intermediate level substitution. It's not a simple substitution because there's lots of little things to keep track of, but it is within the middle of the road type of u substitution problem. I guess, why am I mentioning that? Because what we did last time is now just one little small essential part to a bigger problem, right? And that's kind of what I've been telling you about this class. Everything's building on itself very quickly. So if you've got any gaps with u substitution, then of course integration by parts isn't going to go well. And if you have gaps with integration by parts, then the next technique's not going to go well. So it's the nature of the beast. Are y'all ready to rewrite the integral? Okay, we have integral. All right, we do have, oh, I forgot my du here. Du over here, I forgot to keep it there. we do have a 1 minus -2 over beta squared that comes out. Does someone want to tell me what's next here? Let me call on the next person here. How about Nick? Is Nick around? Yep, I see Nick. Let's see if Nick is present.
Yes, I am here.
Hey, Nick. Are you following up to this point, Nick?
Yes, sir.
Okay, so how does that, I pulled the constant out for you already. What is that going to be rewritten in terms of u?
Is it just gonna be beta squared x squared?
No, let me do something. Let me do this. I'm going to back up just a moment. Okay, this integral, we're rewriting it as 1 over the square root of 1 minus beta squared x squared times x dx. So this blue part is going to be replaced with this. And then the yellow part is going to be replaced with this. Does that help, Nick?
Yes, a little bit.
So let's just rewrite it. It'll become 1 over what? In terms of u.
1 over 1 minus, or no,
Yeah, what are we replacing 1 minus beta squared x squared with?
u.
U. So 1 over the square root of u, right? And then what are we replacing the x dx with in terms of u? All this crap right here, right?
Yeah.
Okay, so I'm going to pull that constant out. And I'm going to leave the du inside. That makes sense, Nick?
Yeah.
Okay. All right, let me see if I can't get through everyone today. How about Alex? Alex Pohl? Alex, are you following?
Yeah, I'm here.
Okay, so how about that integral? You feel okay with that one?
Oh yeah, wouldn't that just be a 2u to the 1/2?
So you already got the antiderivative?
Yeah.
Okay, so just so everyone's on the same page, you rewrote that as u to the -1/2 first.
Yeah.
So you rewrote the root and then you brought it up to the top. That way you could use the power rule. And then you went ahead and did the power rule. And you have to do the 1 over n plus 1, u to the n plus 1, all that stuff. And you got 2u to the 1/2. That's what you said, yes?
Yep.
Okay, good. Plus the constant. We can throw the constant in at the end. And these twos cancel. All right, so remember, we were just doing this, right? And that's what it turned out to be. So we need to come back now and plug this in. X arc sine of beta x minus, now we have a beta here that has to distribute through to -1 over beta squared times what? U to the 1/2, which is the square root of u. And what was u? It was 1 minus beta squared x squared and plus c. So everyone see that? I just replaced that u with what it was up there. I'm ready for a final answer. X arc sine of beta x plus, I'm just going to multiply that through. 2 negatives become a plus. One of those betas cancels. Square root of 1 minus beta squared x squared plus c.
What happened to the beta that we pulled out?
Where? On which one?
Um,
Are you talking about this one here?
yes.
That is here.
Oh, okay.
And then it got passed through right there and just killed off one of those betas. There it is. That's the antiderivative of arc sine of beta x. We could check. I will. Product rule. 1 times arc sine of beta x plus, now the derivative of arc sine of beta x is 1 over the square root of, I'm just going to call it junk from here on out because all that stuff in there is junk. Okay, and then times the derivative of beta x, which is beta. Okay, finished off the product rule. Plus 1 over beta is a constant, comes for the ride. Okay, now I need the derivative of the square root of something. Derivative of the square root of something is 1 over 2 times the square root of that something, which is that junk, times chain rule, the derivative of what's underneath the root, which turns out to be negative beta squared times 2x. And now clean up. 2's cancel. Let's see what happens. One of these betas cancels. And, oh shit, I forgot something. Damn it. On my product rule over here, I did derivative first times second plus, here's derivative second. I forgot times the first right there. But yeah, I think this is good enough. I'll stop here because these two right here are the exact same expressions, just one of them's positive, the other one's negative. Do y'all see that? They both have beta x on top. They have the junk on the bottom, square root junk, they're identical. So they're gone. And that leaves you with this. I just wanted a quick little verification, that's all. All right. $12.20. I'm just wondering if I should show you this one last one. Let's talk real quick about the exam. I already told you last week what to expect, right? A couple of derivatives in the beginning, then pretty much the rest of the exam is integration. Power rule, U substitution is going to make up a huge part of it. And then at the very end, 2 problems, 1 or 2 problems from integration by parts. But I promise you, on the integration by parts, 1 iteration of it. It won't be one where you have to do it twice, okay? Just be 1 iteration, just to show that you know how to use the formula, all right? Does that sound okay? All right.
It won't be anything like this one?
No, it won't be like this one, no. Actually, I mean, if anything, it would be, you know, we're talking about something like, where's the first one? Nope. Where's the first one? Oh, here it is, right here. This one right here. X sine x dx, where you just choose your u, the x kind of vanished away and everything became nice. That's what we consider to be an easy integration by parts problem. It will not be like this one where we have to do it twice. That'll be the next test, okay? Won't be like this where it's not the x you pick, it's the other thing you pick, right? It won't be the natural log. Well, I was just showing you something. Both of these are examples where you have really only one thing to pick, you know? All right. Okay, so that's what the exam is. We good with that? Any questions on that? So I expect, we're not ending class. I just want to get this out of the way now. We'll be here on Wednesday. First thing I'm going to do, once everyone's in, I'm going to email you the exam. I'm also going to send it through the chat here. And I'm going to give everyone about 10 minutes, probably 10 minutes, 15 at the most, to copy all the problems down. All right? And then once you've copied all the problems down, I'm going to say, okay, everyone, put all your stuff away, and you're going to start taking the test, paper and pencil. And remember, you have to have your camera set up so that I can see your entire workspace. So right now I'm looking at everyone's cameras. The way you're set up now is not okay. Okay, and I already showed you all a picture. Like you need like this. You see me? This is what I need to see. I need to see this. I need to see what's in front of you. Okay? I don't need a camera that's going to be like right up to your page. I'm not worried about that. I'm just worried about what things you have around you. All right? Does that make sense? So I encourage you to just use your cell phone, just download the Zoom app. And for the exam, just set your cell phone up in a way that I can see the space around you. All right? The first exam is always the tricky one because we got to get everyone set up properly. So I'm probably just going to look at each camera and I'll be like, okay, Coleman, you're good. Alex, you're good. You know, and I'll just go through, and then the people I don't call, that means your camera's not okay yet. And once we get that all set up, we'll start the exam. You'll work through it. Everyone is allowed to have formula sheets, right? But I told you had to have these already printed out somehow. You're not allowed to look at your computer. You're not allowed to bring up your phone to reference anything. And what I'm going to do, because I can't check your formula sheet, so what I'm going to do is I'm going to call randomly on 3 people. And those 3 people are going to have to hold up their formula sheets to the camera and show me that they don't have anything else written on their formula sheets. Okay? And they're also going to have to show me their blank pages that they're working off of. All right? I can't check everyone. We don't have enough time, but 3 people will get called. And then once that's done, we'll start the test. All right?
Do you have like a recommended amount of pages, like blank pages that you want us to have?
I would put at least 10, 1 for each problem.
All right.
Yeah, it's going to be about 10 problems. So 1 for each problem. And I actually would prefer you turn in 10 pages than try and cram it all into 1. You know, when the exam's over, you have, what you'll do is when the exam finishes, when you're done, okay, when you're done with the exam, you're going to go into the chat here in Zoom, and you're just going to send me a message saying I'm done. And at that point, you can turn off your camera, you can log out. And then you have 15 minutes to get that test to me. That means you gotta get it from paper to pictures, from pictures to PDF files, from multiple PDF files to 1 PDF file. And I've given you all opportunities to practice that at least, right? I sent a folder or a Dropbox a while back. This first exam will be bumpy. If worst comes to worst, just send me what you have. If you can't get it to 1 file, just within the 15 minutes, send me what you have. If it's 8 pages, it's 8 pages. I'll be pissed off, but if you don't get it within the 15 minutes, then I won't accept it. So I just get me what you have. All right. Any questions on that?
Are we allowed to use calculators or like no
Yes.
calculators or?
You may use a regular calculator. It can be graphing, that's fine. I don't care what it is. I want to see your work. Right? That's the thing I want to see. And you have to be real careful, you know, because I know some of these calculators can do antiderivatives, but trust me, I know when people are using these because these things have very strange ways of getting to their answers. And a lot of times the calculator will use, you'll get an answer like let's say we got just now, how did I just do that? I didn't mean to zoom. Like we got this answer right here, and they'll use some weird identities and like simplify it in a way that like no human being would ever do. And so like I look at the answer and I'm like, oh, I know this is not a person. Like, so don't do a bunch of scratch work that doesn't make sense and then just give me the calculator answer. I'd rather you do scratch work and get the wrong answer than to see that. Okay. Any other questions?
Yes, I had a quick question. So I know we were really touch and go with this, but I was looking at the homework yesterday and I was kind of curious if this was going to play into part with integration with parts and other things. Do we have to memorize like the hyperbolic identities and derivatives and stuff like that for the exam? Would there be
They're
like
on your
questions we'll
formula
see?
Those are all on your
Right.
formula sheets. Yeah, so you don't need to memorize.
Oh, okay. I think
You're
you
allowed to have your
mentioned
formula
that.
sheets.
Okay, cool.
Does that answer your question?
I had one more, sorry.
No, go ahead. All these pages, so everyone's clear, all these pages right here, you're allowed to have. Right?
Where do you get them?
Hard copy only. You can only have the hard copy of them.
Sir, where do you get those
They're
anyway
in our
from?
Canvas page under files. Here, hold on. I'll bring it up. I know you can't see my screen. Hold on. There you are. So here's our page, right? Oh yeah, remember that picture right there was me showing you like a way that would be okay on camera. So yours looks a little different than this, but if you go to Files and Formula Sheets, and right here, this right here. Okay, click on that. Now these you can also have on tests, but you actually don't need this test. Starting on exam 2, you'll want to have this one, and then on the last exams you'll want these two. But that one for sure. Any other questions?
Is there going to be any extra credit on this exam?
I will put a bonus problem.
So would that include the 10 questions, or would there be actually 11
It'll
including
be
extra
10 plus
credit?
1. 10 plus 1.
Okay.
And that plus
Gotcha.
1 could really be anything. Like it could be, I mean, most likely it's going to be a harder problem, right? But it could be a harder integration by parts. It could be a harder U substitution. It could be, you know, whatever. Other questions? I was going to give you another example, but I'm not going to because we don't have enough time to work through the one that I want to work through. So
is there going to be like an official like review, or just keep doing the homework?
Yeah, so there's no official review other than what I told you last class. You know, if you've been doing the homework and you've been following along in the lecture and the notes, the problems will be within the same difficulty level. You know, there's not going to be any surprises. Like, oh my gosh, I never saw, you know, he never gave us anything like that. But you have to have been doing your homework, because if you've been doing your homework, I think it's clear that I can work through a lot of problems in class, but there's still going to be stuff in the homework that's going to look like brand new stuff. So as long as you're staying true to yourself about the homework, then everything should be familiar. Now, it'll be hard for me to, it's hard. We talked about this before. There's some intuition with this stuff. You know, you look at the integral and you like kind of just have a feeling of how to approach it. And it's hard to teach that. So what I find on these tests, the things that students get hung up on is like that first step, like that first, like getting the train moving on the problem. So they spend way too much time on one problem, and then they realize that they've been working on a problem for 30 minutes, right? You have 10 problems, you have 100 minutes, and we're gonna have more like 90 minutes. So you don't have 30 minutes for one problem. You've got a little less than 10. So if you're taking the test and you ever feel like, you know what, this problem is, I'm just stuck, I don't know how to start it, just move on, you know, move on. Alex, I don't know if that answers your question, but yeah, there's no like formal review.
Okay, no, yeah, it answers the question.
Do you mind if we like practice sending you that a PDF of like just some?
Yeah, you can do that. I don't know if I'll be able to reply in time, but you can use the Dropbox to practice just doing it. I was actually grading I have college algebra class, and I was grading some of their stuff. And here's a good example. This was a file that was sent to me And you can tell this was handwritten in pictures and it's multiple pages. See that? I mean, that's what I want, because the good thing about this is when it's sent to me as a single file, I'll actually show you how I do this. It makes it so easy. It makes my life so easy, because y'all can see that, right? My OneNote's open. Yeah. So here are all my students. Here are my students. They sent me their tests, right? Now, some of them didn't send PDFs. They sent JPEGs, but I can do, all I do is once I download, I just drag it and drop it in here. And then once it's in here, which usually takes a few seconds, once it's in here, I can write on it, right, and grade it. And then what I'll do is I will electronically send that back to you. So that way you'll, well, actually I won't send it to you email. When you click on your grades, there will be a file attachment there, and you click on it, it'll be your graded exam. So that way you can see what you missed. But if you send me 8 files, then I have to open up 8 different files. It just slows me down. But yeah, to answer your question, if you want to practice, that's fine. You know, I'll send you the actual Dropbox that you're going to use. I'm going to send that to you the day of the exam. All right.
I have a question also.
Yes.
How would the test be graded? Is it graded by wrong or right answers, or like how we do the problems?
No, partial credit, always partial credit. So like the things I'll be looking for, you know, let's say it's a U substitution problem. You know, did you use U substitution? Did you make the right substitution? Okay, now once you made the substitution, did you take all your derivatives correctly? Oh, look, you forgot to carry the 2, right? So there's different levels of right and wrong. So yes, you will get partial credit. It's not thumbs up or down, which is a good thing for you, because there's plenty of room for little mistakes, which I'm okay with little mistakes. I'm just, it can't be it can't be this. Where is it? It can't be this right here. Okay. Antiderivative of x times sine x. Oh, you just took the antiderivative of each one right there. Like, you do that, and I'll find it very hard to give you more than like 1 point just for being able to like put pencil to paper, you know? I mean, because that really shows me that you've lost the main idea here. Cal 2 would be extremely easy if that was the case, right? It'd be a very easy class. Well, not very easy, but it'd be much easier, much, much, much easier if that were the case. So that would show me a complete disconnect. So you wouldn't get much for it. But if you're at least going down some road where it's, you know, you're making some progress and doing correct things, then you have, I guess, I always look at my students as you have full credit to start the test, okay? It's more how many points am I going to deduct? Right, so everyone's starting, like, each problem's worth 10 points. Everyone's starting, you got all 10. Now, how many points am I going to take away? That's the way I look at it. What else you got? Are y'all nervous? Are y'all freaking out, or?
Definitely nervous.
Is it the no review thing? Yeah.
You just need to practice how to send that PDF, honestly.
Are all the grades from this class only going to come from the exams, or are we ever going to have like quizzes in this class?
We're gonna have quizzes, but I think I have us slated for 5 quizzes, and I haven't given one yet. We'll start at some point. I hope. I might just have to do it on participation at some point. We don't have a whole lot of time to. I mean, look at each problem takes us a while, right? And as we progress through the class, the problems will get even longer. So I can't like start a class and say, okay, the first 20, 30 minutes is going to be everyone does this problem. That's very difficult to do. Yeah, so the grades will be mostly exams and participation. I really have been impressed with the participation that I've had with my classes, so that might factor in to the quiz grades. In terms of the review, just to give you an idea, like, I'm not trying to punish you all. okay? I'm not trying to make your life difficult, but I understand that reviews are very dangerous, okay? Because what they do is they give you this false idea that that's the way the rest of your academic life is going to be, and that gives you some false idea of the way the real world's going to be. I mean, if you're an engineer working on some project, you know, and you're tasked with this, you know, figure this out, like there's not going to be like, well, can you give me an example first? Can you like show me like a problem like it so I can go figure that out and then use it to figure this out? That's not, it's about being prepared, and it's about not needing someone to guide you so much. Does that make sense? Like just being prepared for whatever comes, you're ready for it. And so I think when I give reviews, people don't raise that bar high enough for themselves. And you don't learn how to prepare properly if I just give you a review, because then you're just like, I'm just gonna do these problems and I'll be happy. And that's it. If I can do these, I'm good. That's not the way it is. I mean, I could give you 10 problems, ask you to do them, but that's not enough. You need more than that to be ready for the exam. So I apologize. I understand you're not happy about that, but I have your best interest in mind, believe it or not. What else? Anything? Y'all are gonna be okay. You're at home, you're chilling, you're relaxing, right? You can listen to music. So I'm okay with you listening to music like in the room. I don't really want to have headphones. Everyone's audio is going to be off, so you're not going to hear each other. But you can have music on in the room, but no headphones. And that's just because I don't know what you're listening to. You might be listening to my lectures or someone else talk about math. I don't know. So, you know, just headphones in the room. I mean, speakers in the room. Some ambient music is fine. Have your favorite drink, favorite beverage, snacks, whatever you want. All right, well, I'm excited for you all. I think you all are going to do okay. Well,
we'll have the entire class period to do the exam, right?
Yes.
Okay.
I may even give an extra 10 minutes as long as everyone can use that 10 minutes. I'm happy to give everyone an extra 10 minutes. Does anyone have anything that would prevent them from going to like 12:50 next class? Does anyone have something they have to be at or something? No, okay. So I mean, I'm not going to say officially you get till 12:50, but if I look and I still have people working, I'll give you an extra 10 minutes. Historically, Cal 2, more than any class, I usually have people at the end still. Like, I'll always have like a few that finish early, but Cal 2, more than any class, almost everyone is still there at the end. Whether it be because they just went back and they want to look at the problems again and just make sure or double check or, you know, and especially the exams after this one. Like exam 2, 3, 4, those exams, like time is such an issue.
Professor, where do we find the example to send the PDF?
Where what?
Do we find the example to send the PDF?
Well, are you saying the Dropbox link?
Well, not like the actual one, but how we would actually condense them.
Okay, so I never showed you an example. Are you using an iPhone?
No, I have an Android.
Android. Okay, so I used an app I have Android also. I just downloaded an app on my phone. And when I take pictures on my phone, it allows me to take those pictures and make them into a single PDF. And I think it's called, is anyone else using one on an Android?
Would
I'm
we
using
be able?
Adobe Scan. That one works pretty well.
Which one?
Adobe Scan.
Adobe Scan. Okay, mine is called JPEG to PDF. JPG to PDF. And that's just an app that I can use, and it allows me to go into my pictures, select which ones, and then convert it to a single PDF. And then
Would
I
we-
can send that. What's that?
Would we be able to put all the pictures in a Word document and then save it as a PDF?
Sure. Yep. But I mean, the only drawback to that is you've got to get the pictures from your phone to Word, which if you're using a desktop, then you might have to email them to yourself. I don't know. I mean, you can use whatever tools you want to get those pictures to me as a single PDF. I don't care how you do it. I just think using a phone with an app is the easiest. We're going to have some hiccups. It's going to, I mean, this first test, there are going to be issues, all right? People are going to, but just like I said, the most important thing is that you send me at least something, even if it's 5, 8 pictures within that 15-minute time span. All right. Well, I think we're going to call it now. Our test is on Wednesday. I have office hours tomorrow from 11 to 12:30, right? And then before our class for an hour, I'll be around on the Zoom. So you just let me know, okay? All right, everyone. I'm going to sign out.
All right, thank you. See you Wednesday.
Yep. If you think of anything between now and then, just text me or something.
Okay, thank you.
Okay. All right. You'll have a